Okay, boys and girls and children of all ages, welcome to the first programming session of the year 23-24. Hope we've done some work to try to put together a program with which I hope you find informative and useful over the course of the next year. Climate Week, anybody attending any Climate Week activities this week? Yeah? Anyone get arrested? Yeah. No, that's because I think my theory on not getting arrested is most of the people in this room are actually doing something about the climate rather than protesting about it. So just a couple announcements before we turn over the program to Michael and Tim. First, the individual memberships, from what I saw from the numbers, a lot of us have already signed up for that, but there's a considerable savings with, if you plan on attending many of the meetings, $100 is still much less expensive than $140 plus a discount on the gala. Let's see. CEUs, continuing education credits and so on. If you've indicated on your registration that you will be looking to get that for credit for attending this meeting, see Rob Meyer right there. After the meeting, he will have a certificate for you to hand you with your name on it. Let's see. That is pretty much it. And definitely want to mention our corporate sponsors who fund a lot of our work here. Dual Fuel, DNV, Innovative Power, Lados, Npower, Metergy, Utilivisor, Train, NYSERDA, C-Power, Fisher Energy, EIS, EMAX Systems, Aramark, NYIT, Thermax, and two of our newest sponsors just this week, Harris Energy Solutions and Veolia. If your company would like to become one of our growing number of sponsors, you can contact me directly or hit the info email address on the website, and we will get right back to you with that information. And with that, I think we're going to get started and hand it over to Tim with our program today. Thank you.
All right. Thank you, Craig. I'm Tim Lynch, one of the board members, and tonight, decarbonization through electrification has been at the forefront of discussion in our industry for several years now. One significant element of these electric solutions that are being discussed, however, is energy storage, to separate the supply of energy from its demand, the demand for its use. But most of those discussions for storage pertain to battery storage. Tonight, we will discuss thermal energy storage and how it can be an alternative to electric battery storage to achieve these decarbonization goals. Our four presenters tonight will take us from a high-level overview all the way down to a application or of applications of how this can be done. We have Richard Lee, who will be talking about the macro overview of the issue. Lindsay Auden, who will join us on over the internet. We'll talk about visualization of energy and how electrification will kind of better be visualized and how electrification may impact your demand charges. And then finally, we have two engineers from one from JB&B and one from Train, who will talk about the actual application of thermal energy storage to heat and cool buildings. So our first speaker tonight is Richard Lee. He is the visiting professor of physics at Pratt Institute, teaching courses in climate change, building science, and energy systems. He formerly was director of research at the Urban Green Council, where his work included building energy use data, low emissions futures, building code development, and worker education. He's active in the field of energy efficient engineering and system studies and has been so for over 20 years now. He holds a PhD in physics and is a professional engineer and a lead AP. So we'll introduce Richard Lee.
Very hi, folks, and thank you. I know there's a lot of initials after my name, but that didn't stop me. Of course, obviously I work in climate change mitigation, but that didn't stop me from going out in the streets on Sunday with 75,000 friends and bringing traffic to a stop to stress the importance of doing something. So, but wait, where's my show? PowerPoint symbol. Help. Yeah, that's it. Okay, so he's getting rid of the thing at the top. It's gone. Thank you. Okay, so and I'm sure that other thing will go. Yes, it went away too. So the only thing on this that you have to remember, if you would ever like to get a hold of me, or you would like something goes wrong at AEE and you can't find the slides, you can always find me at rlee@pratt.edu. That's all you have to remember. So I'm happier with the mouse. Except, oh, okay, forward. So here's where we are. We have to decarbonize everything, and the only way to do that is to electrify everything. And tonight, I'm going to be talking about the electrification of things in the buildings, but I'm going to assume that everyone knows we need greenhouse gas free power. I'm not going to worry about where we're getting it. I'm going to leave that up to New York State because they are actually the ones in charge of electricity as opposed to New York City. But they have a lot of plans worked out, and this chart taken from the Climate Leadership and Community Protection Act will show you, taken from the Climate Change and Community Protection Act. These are all links, by the way. You can, once you get the PDF, you can go find out what on earth I was talking about. But this chart shows that they really do have a plan for carbon-free power by 2040. And I really hope it works out. But for the rest of the talk, what are we going to do with that? We have to use that electric power for space heat, domestic hot water, and other things. And the only sensible way to use it is with heat pumps. So that's where I'm going to be going. And the first thing came back. Well, I'll just try to ignore that silly thing. And when everyone is talking about how to proceed with electrification, the first thing is to stop thinking about electricity and think about the building envelope. Because the better the building envelope, the lower the loads, the less heat you're going to lose. And that means you can put in smaller heating systems and be consuming less of whatever it is you're consuming, even if it's only electricity. Using less electricity means you have to build fewer windmills, so that's good. So, but better envelopes doesn't change the fact that we still need to worry about how to store either energy or heat or both because we need more at night than we do during the day, and because we need more in the winter than we do in the summer. Now, there's lots of storage systems around that we can call electromechanical. There's batteries, pumped storage. New York City makes good use of the Blenheim Gilboa pumped storage power plant, which upstate provides, I think it's about 1 gigawatt of power. All of these systems work on a daily basis. And as long as you're using them every day, the way I show you in this little diagram here, then they make economic sense because it's a capital item and you lay out a lot of capital and then you have to keep making payments on the loans. And if you're not using something, then you still have to pay for it, and that gets very expensive. So any storage system really has to be used daily if it's got any substantial capital cost. So we've got a big problem then, because we've got a fair amount of energy around, especially solar in the summer, but when we need the energy is in the middle of winter. I'll show you charts on that in a minute, but we need ways to get seasonal storage. So some of you probably know what that means is coming soon, but first, let me just differentiate the two basic kinds of heat pumps. And I'm not going to explain to you how heat pumps work. I assume everybody learned that in school, or if not, you can find it in Wikipedia. But it's the same way that your refrigerator stays cold, the same way air conditioners keep your building cool in the summer, except that they can run in both directions. But in the winter, when you're heating up, you need heat from somewhere, and where are you going to get it? And that's the big differentiation is between air source systems that pull the heat. Oh, stop that. That pull heat out of, I pushed the wrong button. That's the button I wanted to push. That pull the heat out of the air, cooling the air down, pumping the heat into the building. Now, there's an infinite supply of heat in the air, so you don't have to worry about running out. But especially on cold winter nights, the peak load can be substantial because you're asking the heat pump to move the heat up through a large delta T. So there is a peak load issue. Sometimes people who are pushing geothermal systems, as they call them, ground sources, I call them systems, will say that you also have a serious problem with the defrost cycle. That's not true. You do not need a defrost cycle and the associated peak power additions when you're at a design point condition. Anybody know why or why not? It's very cold. It's like 0 degrees F. That's your design point situation. And there is no moisture in the air at 0 degrees F. So there's no condensation on the coils. So you don't need a defrost cycle. You need the defrost cycle when the outside air is at 30, maybe 28, maybe 40, certainly 40, because that's when frost will build up on the coils. So the only thing you need for peak loads is the power that's actually running the compressor and moving the heat. But that is a substantial amount of power in the middle of winter. Ground source systems are more efficient in that they need less electricity. They have higher COPs averaged over the year because the heat is coming out of the ground and the heat there is more like 50 degrees or 55. Come back in a couple of slides to the issue of balance, but you do have to pull comparable amounts of heat out in the winter to what you put down in the summer or do something about it. And because you're using the ground as the place to store heat, you can actually get seasonal storage at a reasonable price. So air source heat pumps have a couple of other issues. The biggest one is that with the popular mini splits, which are ductless air source heat pumps, they require refrigerant tubing going all through the apartment or the building or wherever. And the refrigerant tubing is put together with compression fittings, which are the same things that are used for copper tubing and propane and gas systems and so on. And these are hard to make up. I can vouch for that. I've had to work on them for many minutes to get a leak-proof joint. The trouble is that if the refrigerant is leaking, it's got a global warming coefficient that's 1,000, 2,000, 3,000, depending on what refrigerant compared to CO2. So if we just have a lot of these guys leaking, the value of the heat pump is rapidly eaten up by the global warming potential of the leaked refrigerant. And they leak currently around 4% of what's put in every year gets out. So we need something to do about that. And the best way to do it is to get joints that are brazed in the factory. But in that case, you're going to need ducts or something of that sort. And NYCHA is now testing a better solution, which is a heat pump that is made completely in the factory. All joints are brazed, and the installation consists of having somebody come in, set it in the window, and plug it in. But for ground source heat pumps and seasonal storage, I'm going to go quickly here because Michael tells me I'm already running out of time, but they have a lot of thermal storage capacity, but we have to do something to balance the loads. And one thing you can do is move to Virginia, because there the cooling load is comparable to the heating load, and that'll keep the soil more or less in balance. But if you can't do that, then you're going to want to do something to add some heat to the ground. And one way to do it might be solar collectors. I'm going to show you a slide in just a second. Something that's very rare is to have a water table that's actually moving. But if you do, that will bring in enormous amounts of heat and take them away. So that takes care of it. But the balance is important. And one reason it's important is that there is a misnomer that's used quite often when these are called geothermal heat pumps. They are not geothermal. The total amount of heat coming up from geothermal heat, 50 milliwatts per square meter. If you've got a 400 square foot field, that's about 600 kBTU per year. That's much less than what you need in the heat pump. You're putting more down in the summer, pulling much more up in the winter. The geothermal is just sort of a sidelight. But you can make a system that works pretty well. And these people made a largely solar heat pump system in Okotoks, Alberta, where the design point temperature is minus 27 F. And they have got a collection of heat pumps in their houses, and the supply water for the heat pumps is shared between them and between other buildings as well. And it's pumped up and down into the ground. And in order to keep the ground warm, considering that it's 27 when it's cold, it gets warm enough during the day in the summer. So they've got solar collectors and they heat the ground back up again. They do use some gas, but they get 90% space heat from the solar fraction and half their hot water. Lots of detail here. New York City was impressed by this system and is now looking at a similar project. And the key there will be, of course, that it's got not just a heating component, but a cooling component from commercial buildings. Commercial buildings have dominant cooling loads, so they're dumping more heat into the ground. Residential buildings have dominant heating loads, so they're sucking more out. So if you can use a loop like this to combine commercial and residential buildings, you get a much better balance on the underground thermal storage. And there are plenty of people working on that. Good review article here, hundreds of other review articles I didn't have time to. So, but that's what I mean by here, cooling to provide summer heat. And now I want to touch on some work that talks about the peak load issue from going to heat pumps. And this is some work that we did at Urban Green all the way back in 2013. And we created first a pretty accurate model of New York City as it was in 2010, and found that we were using 51 terawatt hours of electric energy and an enormous gob of gas and oil feeding the heating system. And then we did all kinds of things you can read about in this still available study, but a lot of it's predictable. You probably learned a lot of it in school now, heat recovery, ventilation, all that sort of thing. And we found that we could run New York City on about the same electric energy, but no gas. All the gas is sucked in here. This is all done with heat pumps, of course. And these buildings and this is all modeling done in eQuest. The buildings are not passive house sufficient. they're getting there. They're in that direction, but they're not that tight. And we also did a more relaxed case, which used more electric energy. The key item here is that the peak load in 2010 was 8 gigawatts, but our peak load and it was in July, of course, and our peak load came at 5 or 6 a.m. in January, and it was almost 13 gigawatts and 14 for the more relaxed case. So there is a big issue. And the question is, how do we deal with that? Is it right to go be putting in heat pumps today? And the answer is yes, it absolutely is, because Urban Green Council has gone ahead and done a follow-up, which came out in 2021. I had nothing to do with it, but it was still quite a good job. And the key that they looked at is that today's grid has a peak load from air conditioning of around 11 gigawatts, up from 10 in about 10 years. And what that means is that the winter peak load is now quite a bit lower, and we can increase the winter peak load by about 42% before we reach today's summer peak load. So there's room on Con Ed's grid for quite a bit of heat pump activity. This is sort of indifferent to whether it's ground source or air source. Both are in practice in the city today. But a key thing is that the winter peak will rise unevenly in different parts of the city. And this study has done a great job of taking all the Con Ed distribution areas and figuring out when they will get into trouble. And it will probably come as no surprise that the trouble will come in the least economically privileged areas first, because everything goes wrong in the least economically privileged areas first, right? And they will need more help on improving the distribution networks and the transmission to them and so on. But the fact is that because of this 42% gap, the whole thing will permit careful planning. We can get there with a reasonable amount of expansion, but we've got no real problems until the mid-2030s, and that gives us over 10 years. Gives Con Ed, I guess, and the PSC and so on, over 10 years to be providing the power that we are going to need to be putting in the heat pumps. So 2 conclusions: ground source where you can, and Mike is not jumping up and down yet, so I'm going to add one more thing, which is that the City Department of Design and Construction put out a very good manual on ground source heat pumps about 10 years ago, and they have a model you can use that will tell you whether you're building by building, whether your building is a good choice for ground source heat pumps. And so I think, yeah, that's it. Yes. I'll leave it to you.
Sure of that. I neglected to request that the people on Zoom mute your microphones, please, because it comes across and interferes with the speaker. And also that to hold your questions for our speakers until we will have a panel discussion with them at the end of the session. So please hold your speakers. Hold your questions. Our next speaker is Lindsay Auden, who will appear on the screen. And I will stand over here while Fred does that. Lindsay has been in the energy services business here in New York City for over 40 years and is an AEE member since 1989. He's a certified energy manager, a lead accredited professional. He's authored hundreds of articles on energy issues and trade publications, and in 2017, a book on energy rates. In the late 1990s, he pioneered techniques for visualizing and analyzing interval data that are now used by many of energy professionals in our industry. For over 8 years prior to opening his own consulting firm in 1986, he was energy manager at Columbia University, during which he had won numerous awards, including introduction to the AEE's Energy Managers Hall of Fame. His clients have included many large commercial, industrial, and institutional firms in the New York metro area and across the United States, and in several foreign countries as well. Through National AEE, he has taught over 150 live seminars. In the late 1970s, he produced and hosted over 100 radio shows on energy and environmental issues on WBAI, a listener-sponsored radio station here in New York City. Since 2015, he has chaired his hometown sustainability committee and has made it a leader in several state-sponsored energy programs. He will talk to us tonight about the micro view of electrification and the visualization of energy use and demand charges. Lindsay?
I'm going to do share screen. Is that allowed now?
Yes.
Okay. Hold on one moment. This will stop other screen sharing. Do you want to continue? Yes. Okay, let's go here. Okay, fine. We're going to our blue screen. One moment. Okay, let's go to here. Okay, fine. I'm going to talk to you about what I call minor adventures in thermal storage. In essence, this is some of my experience in the field, in the trenches, if you will. And it's going to talk more about how thermal storage can be applied, as it has been applied in this case, laboratory building and also commercial buildings. So let me just move on very quickly. Hold on a second, where we are here. Here we are. Okay, you've heard all about me. I've done a bunch of stuff, wrote a book, hooray. All right, here's the whole show in 3 minutes. Thermal storage for cooling, been around for over 35 years. It's quite reliable. There are a number of systems in the city and around the country. It is a great way to cut our peak kW demand charges, which, as you know, in New York City are killer. Same thing is true in some parts of California, some other parts of the nation as well. It's also a good way to utilize cheap off-peak kilowatt hours where they're available. Ice needs much less space than storing chilled water. And where we are, there's no space available for anything, so we're going to store ice, not chilled water. But when you store ice, you need a different kind of chiller, something with greater compression. Typically screw compressors in the past. There are some others that can do other things. But standard centrifugals cannot drive down the refrigerant sufficiently to yield ice. So we're going to talk about ice storage. To do it well, to maximize the dollar savings, requires a very good energy management system and automated dispatching. You don't do thermal storage with the janitor running around flipping circuit breakers. It's got to be done and coordinated very well with other plant equipment. Things like free cooling needs to be coordinated with your thermal storage. Likewise, certain other big demands that could occur. And you especially must shape it around your electric tariff schedule. These are basic lessons I'm teaching you right now. So if you forget everything else I said, remember what I'm showing on this slide, especially if you have time of day rates, because in essence, thermal storage for ice in our area is a process by which we can minimize cost. Doesn't necessarily reduce total energy, but it does reduce the peak demand and also cuts the cost, which allows money to be used for other things. And if you want to find ways to trim the costs, however, I suggest you examine your load profiles based on interval data. This is when you look at quarter hourly usage of electricity, not monthly, not annual, but down there in the trenches of detail where you can see how the load changes in short time periods like hours or quarter hours. I will tell you though, and this is the conclusion of my talk when I get to it, not everything always works perfectly well with thermal storage. I will give you one caveat. Even a brief power outage can hurt your bottom line. And we'll talk about that lesson at the end of my presentation. So let's give you some background here. The system that I work with most was for one of my clients in Westchester County, has had a thermal storage system for over 20 years, worked with others, but this one I was with and working on for over 20 years. Here's what it is. It's a 275,000 square foot laboratory. It does all kinds of testing on products. 70% of that space is cooled by the thermal storage system. The other 30% is cooled by gas-fired absorbers, once again, to avoid peak demand charges. The thermal storage system uses 350-ton screw chillers. They make 25-degree refrigerant. That's basically antifreeze. That's what it comes down to. You run the antifreeze through a coil inside these big tanks. It freezes the ice. Whenever you have a phase change, you know you have a great deal of energy being either added or subtracted. So you get a great deal of storage and very, very high density of storage when you go from chilled water to ice. The ice is made in that particular facility and stored in 28 CalMac tanks. If you want to read all about thermal storage, CalMac, C-A-L-M-A-C. These are the guys that have been doing it for 35, 40 years, whatever it is. Each of our storage tanks holds 190 ton hours. That's the rating of it. Actual amount you get is about 100, 110 ton hours. The site annual peak demand, keep in mind it's a 275,000 square foot lab. The peak summer demand is only 720 kW. Peak demand is only 2.6 watts per square foot. And this is what it was even 20 years ago. So you get an idea there how much you can reduce your peak demand, even for an energy intensive place like a laboratory, by using thermal storage to get at that load, which is your chillers. For those who are trying to figure out how this is all done through the tariff, it is Con Edison low tension SC9 voluntary rate 2. For those who are following along in their tariff, it is leaf number 448. Bottom line, it's a voluntary time of day rate you can get if you have thermal storage in your system. However, this kind of tariff, which is ideal in some ways for thermal storage, has 3 separate summer peak demand periods. There's a peak demand period between 8 a.m. and 6 p.m., 8 a.m. to 10 p.m., and one for 24/7. Now, most of you in typical buildings will have the same peak demand for all 3 because it's probably peaking at around 3 o'clock in the afternoon. But with thermal storage, you can shape the load, shape your way in which you handle your need for cooling by looking closely at how you can adjust other loads in the building, other loads of your mechanical systems, so that you minimize each of these 3 peak demand charges and reduce peak load on the grid. One of the ways I found this can be done more easily is through load profiling using interval data. So I'm going to give you a real quick tutorial on this, though I'm sure most of you know this already. When you look at a facility's hourly kW load, it varies with time. A line chart that describes it uses quarter hourly interval data. Vertical axis is your kW, horizontal axis is your time. The peak demand during that 24-hour period or whatever time period you're looking at is, in this particular case, looking at this chart, about a megawatt, about 1,000 kilowatts. There is a base load, which is the minimum for this facility, which is at around 420 kilowatts. And everything under the curve, all the area under the curve is the kilowatt hours. That's your tutorial. Here's what the load profile looks like for that facility when they're not producing ice. Note the large amount of base load, 24-hour base load. You have your air handlers, your interior lighting, and of course your office equipment. This is basically what I call a mountain on top of a plateau. When we talk about load profiling, using topographical descriptions is a good way to get the point across. So what does this look like when we chart it out? The red line is our October 29th chiller, no chiller noise production. On August 22nd, when we ran the chillers, that's our blue line. Everything in between, all that area, is ice production. So you can see this is a lot of the kilowatt hours used by this facility because the ice storage obviously goes on for 5 or 6 months. That's looking at this in 2 dimensions. One of the ways I instruct people is to learn how to do this stuff in 3D, and I've been teaching this for 20 odd years. So I'll just walk through this as another quick tutorial before we get to the point. You can look at your loads for an entire year, 3D, very easily. This is a 3-dimensional load profile for a full year. Again, vertical axis is kW. Horizontal axis in the foreground is your 365 days in a year. 24 hours in a day is the depth of the chart. In this case, our mountain peak is the peak kW for a year. The valleys, those are your weekends or holidays. You can look at these 3D profiles from any different angle, and we are going to flip this around to get a better look at it. So if we have this understanding of an entire year's load, or at least the time of the cooling season, how could we use this to understand thermal storage? And are there ways in which we can look at this kind of information to help our plant operators cut their energy costs? Okay, Here's 8 months of thermal storage seen in 3 dimensions. The horizontal axis down here is your quarter hours of the day, 24 hours in the day. The very first load profile you're seeing is New Year's Day. Then we have, of course, the days that before we get to the cooling season. Still notice our large base load all the time because this is a lab and stuff is running 24/7. Then on top of that base load, we have our mountain, so to speak, the middle of the day, and there's no cooling going on until we get further into the year, close to April. Then that's where we have our chillers making ice at night, but they are off during the day. If we had to take that load of the chillers from the night and put it on top of the day, it would double, perhaps more than double, the total peak load in the middle of the day. But we've moved that load to at night. Now, how do we make sure we got a good control on this? Notice how they operate their building. Very good, tight control. 8 a.m. to 6 p.m., that period in the peak demand charge. They cut off the thermal storage right before 8 a.m. They reduce and shut off everything else in the building they can at around 6 p.m. After that, they turn on 1 or 2 chillers until it gets to about 10 p.m. and then they turn on the third one. And that, of course, wraps around to the midnight of the next day. So they have designed and tried to control their loads around the tariff to minimize their peak loads. But you may say there's something sticking up. What are these spikes that are sticking up here? They are driving the 24/7 peak demand charge. Remember, you have 3 different peak demand charges. This is a system for working with free cooling. What they did was, before I came to the scene, was that they would be running their free cooling by turning on their variable speed fans, opening up their outside air dampers when it was cool at night, cooler outside than it is inside, and to flush out all the heat that had been built up by the continuous load of base load. They would push a huge amount of air in and push it out real quick. But that raised their 24/7 peak demand up by quite a bit. Well, what do we do about that? Here's what August looks like after we pruned those spikes. Now, much flatter. All we did was we coordinated the free cooling with the thermal storage so that they turned on their VAV fans, their variable drive fans, opened their outside dampers, but didn't run them at full speed. Instead, we started them earlier in actually later in the, like I said, earlier in the morning, because they're still before 7 o'clock in the morning, ran them at slower speed. Remember your fan law. You cut your speed in half, you cut your kW by 3/4. That's approximately what we did here. And that cut down their 24/7 peak and saved them more money and also reduced load on the grid. See how flat this curve is? Look at how flat these load profiles in August, when normally you would have a big spike in the middle because of running your chillers in the middle of the day. Now, let me sort of get to the end point here of telling you where things don't always work with thermal storage. And this is an unfortunate situation that we call the really big oops. Hopefully this will never happen to you, but it did happen here and it was quite a good lesson to learn. To understand the lesson, let me first set up the situation for you. Imagine a month of July many years ago, and the month of July, of course, has different billing periods within it because we never start exactly on the first day of the month. So here, our black hatched area is the July billing period in that month, and right near the end of the month, we have our August billing period starting near the end of the July and then going on into August. That's very important to understand because of what occurs. And also when you design your thermal storage systems, you have to work it around how you are billed as well as how you operate your building. In this particular case, the July billing period ended at noon. See the black dashed line in the middle? That's where it ended on a Wednesday. The red square, that's a Wednesday. However, a power outage, the red squiggly lines you see, that power outage, which was localized, it only covered a few blocks. It was a feeder that went out in the underground. That ran from Tuesday afternoon into early Wednesday morning. So no ice got made Tuesday night. So what are they going to do to cool that building when people come in Wednesday morning? Well, they had to run the chillers all day Wednesday to cool the facility. That meant that July's peak demand occurred Wednesday in the first half of the day, and August's peak demand occurred in the second half. All because we had a power outage right near the time when we got to the end or beginning of our billing period. The end result was that 2 months of peak kW savings were lost from one ill-timed outage. Keep in mind that we're trying to control this only for about 6 months out of the year. They lost almost a third for that year of their peak demand savings. That's just a lesson to let you know that we work around the tariff, and to get biblical, the tariff giveth and the tariff taketh away. So understand, when you're running chilled water systems and ice storage systems, you better be sensitive to what can happen if there's a power outage. And I see my time is almost up. So I would just say thank you very much for your time and attention, and hand the situation here back to Mr. Bobker. I will stop sharing at this point. Thank you very much.
Thank you, Lindsay. You will be sticking around, I hope, for the panel session.
Sure.
You'll have more of a prominence, actually, than the 4 speakers or the 3 speakers and moderators sitting in front of you, but that's good. Our third speaker tonight is Tyler Schott. He's a senior project engineer with JB&B Deep Carbon Reduction Group, the DCRG, as they call themselves, focusing on project management and building energy systems analysis. He is adept at developing energy models that provide invaluable insight on a building's overall energy performance and inform recommended measures to reduce carbon emissions and related costs. Along with his energy and carbon-related work, he has considerable experience in HVAC system design, drafting, and direct management of small-scale projects at the firm. Tyler holds a Bachelor of Science degree in Mechanical Engineering with a minor in Energy from Lehigh University in Bethlehem, Pennsylvania. Tyler?
All right. Thank you for having me. Appreciate the introduction. Again, to repeat, my name is Tyler Schott. I joined JBV about 4 years ago, and we started this deep carbon reduction group, where all we focus on is decarbonization and practical solutions, specifically for the built environment. So it's been a pretty fun journey. Today, I'm going to hopefully marry 2 subjects that we just talked about, heat pumps and thermal storage together, and how that can be applied for, well, we just talked about cooling, but now we're going to try and apply that for heating. Hopefully. There we go. Okay. We're actually going to start with a video. This was a video that was produced by my firm. It's about 5 minutes long. Once we conclude that, I'll kind of drive into some of the high-level concepts we'll talk about, and actually what we're calling ice heating and how that works. And then obviously we'll have follow-up Q&A afterwards. All right. So hopefully if I hit next, this should work.
Hi, those of us on Zoom have lost the audio video of the presentation. We can still see the room.
All right, so hopefully that was a good introduction. I understand some of you may want to do a rewatch on that. It's on YouTube. You can search for it. We'll obviously send the link out so we can do a repeat of that video, but hopefully the slides I'm going to go through is going to kind of break that down a little bit more. So the fundamental problem that we face as engineers and an MEP firm, and specifically here in the densified city of Manhattan, is this problem right here, where we have an existing boiler or a brand new boiler, and it's traditionally burning natural gas, some carbon emitting fuel, and we want to do an electrified switch to a heat pump. The biggest problem is you can't do a one-for-one like swap. We just talked about the drawbacks of the air source heat pump. It's big, requires a lot of air. It just physically won't fit in these spaces. So one of the things that we have to do is we have to decrease the size. I'll give you a second. Yeah, no problem.
Craig, you lost the Zoom altogether?
No, the Zoom is there, but it's just showing,
It's showing Lindsay Auden.
Yeah.
Name.
It's only supposed to dominate over the panel.
There we go. That should work, right?
That's better.
That's all right. Okay, hopefully we're okay.
back in business.
Off we go. So the fundamental problem that we have when doing a like-for-like swap with an existing building or even new construction, or when we do our heating load calculations, right? We always just want to have one piece of equipment that meets the entire of the load and move on. When we look to do an electrified swap with mostly an air source heat pump solution, right? That's a real challenge physically because those heat pumps require outdoor airspace access. So hopefully. Okay, so I'll talk about the basics and how this ice heating works, right? I'm going to take you on a little journey. We'll talk about the concepts. So as Chris mentioned in that YouTube video, ice is essentially a liquid water with the heat removed from it, right? So if you start with a cup of water, right, and you extract the heat out of it, it will eventually turn into ice. Some of us are familiar that it's an excellent phase change material. It's about 144 BTUs of heat content for every pound of ice that you can extract in that phase change. So the analogy that I like to use is how many of us have ever stuck our hand behind a refrigerator or a freezer, right? It's kind of hot back there. Even in the middle of winter time, you're still refrigerating your food. It's still letting out some heat. So if we look at this analogy, right, we could start with a cup of water, right? As I mentioned before, everything has heat in it. Ice is no, or water is no exception. Anything above absolute zero is technically hot. If we stick that cup of water and we put it in our refrigerator or a freezer, right, that heat will be extracted out. That refrigerator acts as that piece of equipment or mechanism that removes that heat. And then that heat is actually rejected out the backside of that refrigerator. So if we scale this analogy to equipment that we're familiar with in the commercial HVAC industry, it might look something like this, right? This is our ice heating arrangement, where we actually start with the ice tank, right? It's actually just a big tank of water. That's how it usually starts. And if we apply a ice chiller or a glycol chiller that makes ice, right, we will pull that heat out. In traditional cooling systems, that heat is usually thrown out of a cooling tower, right? There's some associated mechanism where you can dissipate that heat. In this arrangement, we are not going to throw that heat out. We are going to distribute that water, usually through a hydronic system, to a heating load inside the actual building. To understand what this looks like in an actual load profile. So in Lindsay's presentation, we looked at load profiles typical of summertime. What we want to do is look at load profiles that are typical of the heating. So here, if you look at the light blue dashed line, I have a 3-day February heating load where you can see the morning warm-up spikes that are typically occurring at 7 and 8 a.m. And the load increasingly goes up over time as the temperature goes down. So how we deploy this ice heating system is we first start with the air source heat pump that provides the heating that you need for the building up to some midway point, right? It's usually whatever capacity of heat pump that you can fit on your roof, right? So you operate that you operate the heat pump up until however many heat pumps you have. And then to kind of fill the remaining bucket of heat that you need, you can deploy the ice heating solution. So you can deploy that ice chiller, which is also a water source heat pump, and you can fill that remaining load. Now, one of the interesting things that was brought up in the video, but may not be inherently obvious, is that once you've depleted your thermal battery, there is a way to recharge that. And you can do that with your actual air source heat pump. So I'm showing here the orange area, which is indicative of the air source heat pump, right, operating to effectively melt the ice tank, right? That's a way to recharge that thermal battery. And you can do that in the off hours. So this system is really all about shifting this load similar to cooling, but now we're in a heating application where you shift the load from the daytime to the actual nighttime. Now, I want to harp on why this is important in the first place. So you shift load, you do all this work, right? You can play a tariff game, which I think is very interesting. It's very applicable for summertime. Tariffs are a little bit cheaper in wintertime, but the effect is still the same. The key differentiator for why ice heating is important, especially in the New York City market, is you have the ability to reduce your heat pump quantities and capacities. So a typical designer, right, he'll do his load calculation. He'll pick the lowest temperature day according to ASHRAE. He'll reduce all of his plug loads, maximize occupancy. It's the morning. And he says, you know what, I need 7 heat pumps in order to meet that load. That's going to be that tippy top condition all the way up there. Might add some factors of safety, right, to account for any worst case conditions. But when you deploy the ice heating solution, you can actually reduce your heat pump plant down to, in this theoretical condition, 4 quantities. So that's about a 40% reduction in equipment and basically saves a lot of roof space. All right. So what that would look like in an actual roof, right, when we go to design this system, right, a typical design would have 7 air source heat pumps and it takes up all of your roof space. Right, you can see there you have the cooling towers, you have the core area, and then you have these 7 air source heat pumps. But when you deploy ice heating, you can now only use 4 air source heat pumps. And all the other equipment can live indoors, anywhere in the basement, existing mechanical room. You don't need that access to outdoor air like the heat pumps require here in this scenario. All right, and to kind of highlight why this is really important is when we're actually at the drawing table with property developers, with the building designers, right? Telling them that they can install an entire electrified solution, but they need half the equipment that is normally required. This kind of becomes the sell point, right? This crosses that go, no-go decision-making where you go, yep, I think I can do it. One really interesting example is the new 270 Park Avenue building, the JP Morgan Chase headquarters. That is an all-electric building, but they did not do ice heating. What they did is they designed, right, for this peak condition. And what we discovered through this lessons learned process is that it was a huge impediment to design. It was extraordinarily expensive to do it this way, right? So taking that lesson learned, if a property like, or even a building that big had deployed something like this, or maybe even in the future, they could use a lot less air source heat pumps, right? They can deploy this methodology of reducing that equipment account. So the key thing here is that it frees up space for other amenities, right? Maybe a property developer wants to have rentable square footage as in a new amenity space, right? That's very valuable. That's freed up space, all right? And at the end of the day, it can almost mean the decision-making point for whether electrification of a building, existing or new, actually happens. So some key takeaways, right? Ice heating is all about equipment sizing. We want to reduce the peak loads. We want to reduce the quantity capacities of air source heat pumps. When you go to operate the system, you can play with time of use carbon emissions, right? We know with New York State's onboarded renewable energy systems, solar, wind, right, coming from the upstate Buffalo and even from Quebec, right? We can now basically play with and have a grid interactive building where we can mess with the time of use carbon emissions and even the peak shaving, right, to help save some dollars. There's obviously a pretty significant amount of controls, logistics, and smarts that goes behind this system. But it's kind of our way of advertising. This is a key way to unlock electrified buildings here in the densified city of New York City. And I think that concludes my presentation.
Thank you, Tyler.
All right, you're welcome.
Okay, our next speaker is Patrick McBride, Train Corporation. Patrick is a Penn State graduate with a BS in mechanical engineering. He's been with Train since 2017 and holds various roles in having held various roles in product. I was waiting for that. Product engineering, quality reliability engineering, and in his current capacity, he serves as a sales engineer in the New York City area. His primary focus is designing high-performing equipment within high-performance applied systems across all vertical markets. In his free time, he's an avid golfer, but not a good golfer, he says. Okay. And still working towards his first hole-in-one. Well, he also spends time enjoying with his dog. Patrick. So, floor is yours.
Not quite the accolades as my predecessors, but I swear very passionate about topics that we were talking about and why we're all here. So again, Pat McBride, I work for Train Commercial Sales. I'm a sales engineer, primarily deal with MEPs in the city, so a lot of design work of high performing systems. So Tyler described it as ice heat. We call it storage source heat pump. It's the same concept that we're here to talk about. There you go. But my focus is going to be a lot more on system drivers and equipment, limitations and why we choose to use some over others. Talking about systems as a whole, So here's our agenda. Local drivers, building decarbonization, some of the financials and some of the system level considerations, a specific storage source heat pump, and then just to wrap up the entire night tonight. So why are we here tonight, I like to think that everybody in this room, including myself, has a vested interest in decarbonization as a whole. Otherwise, you're not here, I like to think people aren't just here for the credits. Maybe we are, but hopefully we're learning something out of this as well. So decarbonization. Decarbonization is this effort to reduce the amount of carbon that we're putting out into the environment. We know that this magic number, if the Earth raises temperature by 1.5 degrees Celsius by 2050, bad things will happen, So our overall goal and a trend is to look to reduce the amount of carbon that we are putting out into the Earth. I show up here, Local Law 97, As I said, we all have a vested interest. Some other people may not have an inherent interest in doing this, So local legislature has pushed us into a trend towards decarbonization. At Train, we have categorized 4 pillars of decarbonization. One is higher efficiency equipment. Another one is refrigerant management. Another one is renewable energy. And then the fourth one is electrification, So what we're here to talk about today is one of the many, many solutions that are out there, which is a fully electrified solution, It's important to know that what we're talking about, storage source heat pump or ice heat, is not a one size fits all. It doesn't meet every single application, every single building, every single owner. It's just one of the many options out there, So heating with heat pumps, It is a winner, And so we're specifically talking about air source heat pumps. But what are some of those challenges of looking at air source heat pumps, right? So balancing, right? Loads are not always equal, right? This says we might have to missize a plant to accommodate for one of the loads and not necessarily the other, right? This could be a waste of space. This could be a waste of funding. This could be a waste of electricity and efficiency within a system, right? Balancing is certainly a tricky subject. Colder climates, right? So New York City is certainly one of those, but as we move more into the Northeast, if we move up into Canada, right, some parts of Europe, we would call really cold ambient climates, right? Air source heat pumps have limitations when we start getting into really low ambience, and we're going to talk about some of those. Space for heat pump outdoors, right? Tyler mentioned that, right? So air source heat pumps, because you need to pull heat from ambient, and if we're talking about 0-degree ambient, we require a lot of surface area. This means we have really big equipment that we might not have the room for. New York City, very specifically here, right? A lot of times we have really large buildings that are 50 stories tall, but might be half a city block. So we don't have a lot of real estate outside that we can pull heat from, right? Our ambient air, right? So space is certainly critical when we're talking about air source products. And then overall air source heat pumps are generally more expensive than what we would say are water source products. So water source would be things such as centrifugal chillers, water to water heat pumps. These are generally less expensive than air source heating products. And we can talk a little bit about that as well. Right. Heating in cold urban cities, right? Let's talk about New York City specifically. Replacing gas boilers with electric. If we were to do 1-to-1, whether that's gas boilers to electric boilers or gas boilers to air source heat pump as a true 1-to-1 from a capacity standpoint, again, cost prohibitive, space prohibitive. But then if we also take a look at electric heat, right? If we go from just gas to electric, it could drive up what peak demands. If we start looking at heat pumps, it starts to work a little bit better because we're working off the concept of heat of compression. And we start looking at COPs being a lot higher than 1, which would be just electric resistance. Heat pumps a lot of times might be in the 2s, the 3s, the 4s, depending on ambient and depending on some of your conditions if you're looking at water source. Ground source heat pumps, so that's GSHP. A lot of times it's restricted by what we would say underground infrastructure, right? So in New York City, we have hundreds of feet of subways, of electrical, of plumbing, of gas that would prohibit us from drilling down and doing ground source heat pump. If we move outside the city, well, we would say, well, maybe we go around some of those limitations. Ground source is still a very viable option, but has a limitation in that it is very financially intensive, right? It requires you to drill very deep down, have a really large bore field. It can be a very high performance system, but from a financial standpoint can be pretty intensive. Air source heat pumps only, right? So a plant that is truly air source heat pump certainly has its limits, right? Ambience. You may need additional heating in your space, right? Via electric. If you get to situations where you're below a given ambient operating range, you might even need backup carbon-based fuels. There are ambient and lift limitations. So what that means is there's certain points where air source heating products do not operate in a given ambient temperature. And then lift is a concept of at a given ambient temperature, what we would say is your source of heating, how high up you can raise a temperature, right? So how high of hot water can you produce? So there's certainly limits within the air source products. Defrost derating, we heard about this a little bit. So this would say when there's moisture in the air because we have are pulling heat out, we may form ice on a coil and we have to consider defrost within our sizing of systems, as well as limited roof space. We acknowledge that they are big. We don't have a lot of real estate and we might not be able to fit them. So here's a concept about limitations of air source heating products in relation to ambience, right? So a general trend that you will see is that commercially available air source heating products will cut off at about 0-degree ambient. They may operate a little bit below there, but are rated to 0-degree ambient. That's most major manufacturers. There are some companies out there that are doing technologies below there, but are not, right, what we would say commercially viable. Trane is one of these we are developing for ultra cold climate ambience, but it is not something that's currently on the market. The other trend that we'll see is when you look at certain temperatures of hot water that you're producing, as well as the ambient that you're looking at, there are derates to your system, right? So one, this would say, as you produce hotter hot water, and as you go to lower ambience, that generally means that you're not going to be able to get as many BTUs out of an air source product, and your equipment is going to become less efficient, right? So in New York City, we would say our design temp is 13. A lot of the MEPs in this city will design around 0 as a safety factor. That puts us right at a cutoff point for a lot of air source products. As well, it says we're going to be a little bit less efficient than water to water products. So here's where this concept of storage source heat pump comes in, right? So this mixes air source products as well as water source heating products, right? So Tyler took us through what the concept looks like, but here are some of the high level advantages of ice heat or storage source heat pump solutions, right? Energy efficiency. So we're talking about COPs. If we talk about air source products only, at low ambience of 0 degrees, we might see COP, a coefficient of performance, in the high 1s or the low 2s. If we start talking about water source heating products, which is where we're generating a lot of the heat in these systems, right, via the ice, right, building ice and pulling heat out of that using water to water products, we might see COPs up in the 3s, up in the 4s, depending on temperatures that you're creating, right? So you're all of a sudden talking about an increase in overall system efficiency by creating better conditions for your equipment to operate in. Reliable operation, we would say, because we aren't reliant on ambient conditions, as long as we have water to pull heat out of and build ice, we have a reliable source of heat. And as long as we can put that out into a loop within the building, our water to water products will be able to build heat. And so all of that comes into sizing of a system, but it is a good way to have reliable heat throughout a system. Save roof space, right? We already talked about that. It's a good way to reduce the amount of air source heating needed on your roof. Higher supply water temps. I'm going to go into this, right? Water to water systems, equipment, they are capable of making temperatures upwards over 200 we're seeing now, right? So air source products might be limited at about 130 as a commercially viable solutions. We're seeing some water source systems being able to make 225, 250. And overall, lower costs. I don't want to say this as a blanket statement. This is, again, an asterisk. It depends on the system, on the application, but you can look at things such as rebates, right? So a lot of times heat pumps in general will have rebates, but overall, if you look at really high performing systems, right, your utilities such as Con Ed, your groups such as NYSERDA, we looked at, right, on a national level, the Inflation Reduction Act had things for thermal storage. There are methods to look at financial savings that help paint an overall picture for storage source heat pump. So here's a concept for thermal balancing, right? So here's just a 48-hour snip, looking at an identical load just to prove a concept here, right? So here's the thought process around using thermal storage for building ice and then also melting ice, right? So we would say the red line is going to be our heating load. Blue line is going to be our cooling load. So what we would say is you can see the peaks for heating. You can see the peaks for cooling. On the left, underneath, right, our shaded area under our cooling load, this is going to say we have a cooling load. We have the ability to pull heat from our building. This is available energy to store into our thermal tanks, right? And we're storing by melting any ice that might be in those tanks. Because what that's going to allow us to do then is when we have a heating load, now we have stored energy via water, and we're going to pull that energy out and use that for our heating. And then what that does is, right, it just flips back and forth.
Just to clarify, this, you're modeling or you're suggesting this is a typical office building that has an interior zone and external zone.
Yeah, correct. That's a good clarification, right? A typical Class A office that's going to have perimeter heating loads in the winter, that's going to have interior cooling loads year round, right? We would traditionally see a load profile like this. And what we would say is you have the ability to flip-flop where your heat source and where your heat sink is within a building. Here's a slide that I want to show some of the limitations about air source products, right? So here is one of the operating maps of one of our air source products. This is using a new refrigerant, 454B. You can see that right at higher ambience, we got the ability to make up to 140 degrees. But you'll see this starts derating the ability for the hot water production around 55, 50-degree ambient. And we can operate down to 0, but you can see at 0, at a full load, we might only be able to make 90. At a part load, we might be able to make 100-degree, right? We have some products that can do this up to a 30 in air source, but we know a lot of the buildings in New York City might be designed around 180-degree hot water, right? So what do we do in this instance? Well, like I said, water-to-water products have the technology to be able to get you up to those elevated water temps that you need to, right? So as soon as we go down below where air source heat pumps are capable of operating, this is when water-to-water heating equipment becomes really viable, right? Not only, right, as long as we agree that if we have water and we can pull heat out of it, we can operate at any ambient we want. As well, we'll be able to make temperatures higher than what we would with air source products. This is, again, a slide to kind of reiterate. Tyler talked about this a little bit as far as what we're looking at when we say downsizing your air source heat pump. So what I want to clarify with this is, right, if we take a look at this, this is a building load and a heating profile across 24 hours, right? And let's just say this is another Class A office space, right? Our peak day heating load at 7 a.m. might be 12,000 MBH. Right, what that would say is if we're looking to accomplish this with all air source heating products, it would mean that we need roughly 10 of our air source heat pump units, right? That takes up a lot of roof space, takes up a lot of energy as well. Instead, as an alternate, we can size our air source along with our thermal storage tanks to provide roughly half or 40% of the heat needed, right? So what this means is that it's not saying that our production side, but what's actually producing the heat for the building would drop below that 12,000 MBH. But what it's saying is that where we are getting the heat from, which is the ambient air, right, can drop down, right? So overnight, right, we can melt the ice tanks via air source heat pumps. And then as long as we have enough storage to account for the half, and half of being air source heating, then we can have enough heat source to then provide to our water-to-water products to then feed the rest of the building. With this, right, this is somewhat of a newer concept, right? And I think a lot of thoughts when I first saw this as well was that this is complicated. I may not want to do this. I don't understand it. What there is to say is that there are a lot of companies out there, right? Trane has simple models to help you out with this. JB&B has a full team to help you out with this. There are companies out there that are looking at this, that are developing tools to help you with the analysis. Like I said, this is not a one-size-fits-all. It depends on the client's drivers. It depends on the building that you're looking at. It depends on where you're at. But there are many tools out there that help you do financial modeling, emission modeling, footprint modeling, right? So overall in your space. Here's something that's interesting, right? We took this from a 300,000 square foot office space. We just took an identical profile, but compared it across Chicago and Buffalo, right? So a dirty grid versus what we would call a clean grid, something with renewables. A lot of clients have been asking us to take a look at what we're calling, right, the embodied carbon, the carbon emissions, as opposed to just your utility usage. So we took average, right, CO2 per megawatt hours in these areas. And based on these profiles in different areas, we compared a storage source heat pump project, a true just full gas heating, a just electric resistance heating, and then a just air source heat pump heating. And you can see with this given application, a general trend that said overall a storage source heat pump was a more carbon, or I'll say a less carbon intensive solution overall, right? You can see a drastic comparison compared to full gas heat, seems obvious to us, but you can even see a very good reduction just compared to the heat pump, all air source heat pump. That's due to the concept of our water-to-water equipment, again, has much higher COPs and are significantly more efficient pieces of equipment than just air source products. And you can see, right, the difference as we look here in New York City, right, New York State, The intention is that our grids are going to get progressively greener and greener with renewables. And we're going to see that, right, as we use more and more electric products, we're going to see our carbon output go down with that. One really unique thing that I'd like to highlight, right, as I wrap up. So this is a project that Trane is currently working on. So up in our corporate headquarters up in La Crosse, Wisconsin, we basically said that, hey, if we want to prove this system, what better place to do this than in the middle of Wisconsin, where it can get to negative 20 degrees ambient, right? If you can do it here, you can do it everywhere. And something tells me our corporate people stole that from Frank Sinatra, but we'll let that one slide. Right, so you can see this is a training center that we're retrofitting with one of these storage shores heat pump systems. We have a 180-ton air-to-water heat pump. We have two 110-ton nominal chiller heaters. These are screw machines. We got 7 thermal ice tanks. And then we do also have a trickle heater, and that's important. Right, so what that says is we have our air source heat pump, which can operate in cooling or heating. What you'll notice is that there is no cooling tower on this building. So our air source heat pump will operate in cooling in the summer. Our two 100-ton chiller heaters are just going to operate as heating products. So they're not going to be cooling chillers, just heater products, which are going to pull the heat from our 7 ice tanks, right, to produce heat for this entire building. The trickle heater there, what that is let's say we get into a situation where we don't melt all the ice, or we get into a situation where ambients are really cold and we don't have the ability to use our air source product to melt ice. We have backup via an electric resistance system to be able to melt that ice. Again, the entire driver here is that we want enough water within our ice tanks to be able to pull that out throughout the day. So overall, right, this is a very unique system that we're hoping to put up, I think, by winter of 24. We'll be happy to report out on what this looks like, right, the success of this, and what some of the system performance looks like as we do this. But wanted to showcase a very real system where we are putting storage source heat pump into practice. With that, I'll wrap up. If anybody has any questions, I think we're going to do a panel, but I appreciate everybody's time and attention today. Thank you.
Thank you, Patrick. And a quick round of applause for all our. Up to the podium here and join our nice speaker from.
Sitting?
Oh, there we go. These microphones up there.
Stress when we pull it out.
No, I think it'll pick up this microphones in the ceiling.
I won't be shy.
So thank you, gentlemen, for really interesting presentations. They play off each other really well, I think. Craig, I want to ask first if our online audience has questions.
We had one question for the first speaker to let everyone know what that study was being referred to, the city study. I think it was probably the urban green studies.
BBC manual or?
Can you clarify the question a little more?
I'm trying to find it again.
You had 2 studies, 2013 and one that was 20.
It was, if Andrew Piper is still online, the question was, can you repeat the NYC study that you just mentioned?
Oh, wait, I'm sorry. Yeah, I don't think he's referring to either of the 2 early ones. They are both have links to them in the PDF. So you'll be able to find them. But at the end, I did mention a study. It's not in the visuals. And that was done by the New York City Department of Design and Construction. Excuse me. It wasn't really a study. It was a handbook of how to do ground source heat pumps in New York City. And then growing out of that, they have a computer model that you can use online put in the address of a building, it will find the building, and it will give you an assessment of whether the building is a good choice for ground source heat pumps or not. And I don't have the links for that, but if you put it in a search engine, New York City Department of Design and Construction, ground source heat pumps, I'm sure you'll get there.
Okay, great, thank you. And you should mention that the presentations tonight will all be posted on the AE website in single digit days.
Did everyone hear that? The presentations will be posted, so you can get this. Okay, audience questions?
Question for Richard. You mentioned earlier when you have a seasonal imbalance between heating and cooling loads within a geothermal field, that it can be necessary to have either additional heat rejection or heat acquisition, say with solar panels. Can it also be solved in part by simply enlarging the field? Digging deeper, more wells, or does that just become an uneconomical solution?
Well, I think the answer is an economic question. How much is it going to cost to make it bigger? Now, if there is a serious imbalance, if this is just a residential area, so all you're doing is sucking heat out to heat buildings, then what's going to happen is that the ground is going to gradually cool. It's cooling a little bit every winter, but then it warms up again with some air conditioning load. But if you just keep doing it, then year after year, it will be dropping in temperature slowly. And this is very basic physics. People have done very decent calculations on it. And if you don't, what will happen is just the efficiency of the system will get smaller because the source of the heat is getting cooler and cooler. I can mention an excellent source for calculations on this sort of thing is a book called Renewable Energy Without the Hot Air. And it's a terrific book. The book's this thick, but you can download it for free online. And it's got all kinds of calculations of this sort of thing because the guy doing it is a prominent foreign, unfortunately deceased, but he was a prominent British physicist at the time.
Thank you.
Do have another question online.
Okay.
Can you talk about how higher capacity chargers and changing coincident peak times on the grid will impact the potential for ice storage? It's getting harder to predict these peaks around the country.
So I think, Lindsay, can we turn to you first for that topic? You're the rates expert.
So the question is, concerning only capacity factors. I'm sorry, ICAP charges and how they influence the viability of heat pumps. Is that the question?
Yes, and if not ICAP specifically, in some areas of the country, just hitting coincident peaks, affect whether it's demand or capacity. Yep.
Well, this gets to the very specific ISO you're talking about because they all have different capacity charges and different characteristics. If you're talking about, for example, the mid-continent ISO, you've got a lot of very, very cold weather there. That's a very different situation, and at the same time, they have relatively low capacity charges. So you got to be very specific which ISO you're talking about. But let's just talk about New York ISO for the moment, okay? And where we are. We have high capacity charges, especially down where we are here in the lower portion of the state. That may change as the different new transmission paths come about. And I think that you have like several different characteristics going on at the same time. I don't know exactly how it's all going to shake out in the end, but I will say that once we switch to a winter peak, situations may change drastically because there'll always be, in my opinion, some gas-fired heating at that point, and that's what's going to drive the overall price and at the margin. And capacity factors have a lot to do with what is available online on the grid in order to make sure the lights stay on. So bottom line, I think you have too many factors coming together at one time and have to be very precise as to which ISO and which time period you're talking about. Because as you go forward in time, capacity charges may go down depending upon the amount of renewable power we get in. I will warn you though that wholesale electric prices, even now, because gas is the price maker, we have a winter peaking charge for the energy, not the demand, but the actual energy. And January and February have been very high. And if we go to more of a winter peak with heat pumps, the viability of heat pumps from an overall perspective of how much they cost to run may be very dicey for a while until more gas comes off the system and the price maker at the hourly level is no longer tied to the price of natural gas. Because the problem is natural gas price goes up in the winter, just at the same time that heat pumps are going to be working harder. So you've got multiple things, and it's not just the capacity factor, it's the cost of the actual energy, wholesale energy, because of its interaction with the continued use of natural gas as a price maker. So bottom line, I don't think there's a way to come up with a good answer to that until you look at all the factors combined together.
And then just as a follow-up, if the peak loads were to shift to winter, and peak demand charges shift to winter, would that have an effect on the viability of thermal storage?
I think for heating, yes, I think it may. For thermal storage for cooling, that's not going to get too much impacted. But for heating, yes, because once you start to make yourself more dependent on electricity as a source of heat, not cooling, but heat, you begin to become more vulnerable to whatever else is going on the grid that may impact what your costs are. I just think that this is why you need to look very, very carefully at your tariff, what you can get away with, and also how you purchase your electricity, whether or not it's going to be on the wholesale, like straight from Con Ed, where you are not immune from the vagaries of the market, or through some sort of temporary fixed price, or at least a cap and floor price, so it never goes above or below a certain point, and buy that through a contract. And I'm not going to get into all that detail, but the bottom line is you need to look at other factors other than mechanical to maximize your savings.
So Tyler, Patrick, I hope you were thinking about this question Lindsay was talking, because I think, as we heard from Dick, there's quite a bit of heating side capacity where we can still grow before we have to worry about switching over to a winter peak. And early movers in the direction that you're suggesting will have systems like this that will still be looking at summer peaks. So my question to you is, we heard about how the system works, why what's being proposed for heating with ice is being proposed. How will these systems work in the summer? Will they work pretty much the same way as the typical as the thermal storage in the summer, the way Lindsay was describing it? Is that what we will see in the summer mode?
I can take this. So we have a lot of capacity to grow in the winter time. It's probably going to take 20 to 30 years. I think the worry is a little premature. Right now, we understand the controls for ice heating is probably pretty complex. To Lindsay's point, a janitor cannot run this. And it will require kind of the next level of building operators who have the intelligence and the automation capabilities to run ice heating. The technology's the same, right? We're talking established legacy technology. It's just in the matter of the arrangement and the way you control it is the innovative part. And that's where the development needs to occur. And we're not quite there yet. The right application now for ice heating is an existing building that already has ice storage that they use for cooling. And now it's a matter of rearranging some pipes, control strategies to basically deploy ice heating. That's right now by far the easiest and best way to deploy ice heating solution. What we've also discovered is that any ice tanks you have, say an existing building, if it's applied and designed correctly for cooling, we are estimating you only need about half of those tanks to operate properly in the wintertime. For the smart people in the room, right, we all know that we can take advantage of the compressor heat that's involved in the heat pumps. Right, so there's that added level of BTU that you can slap on top of your heating, where you don't get to slap that on in a cooling mode because you have to actually reject compressor heat. So by and large, that's all to say is full capacity in cooling, about half of that is required for heating.
So if you've designed your system, your storage system for heating, you're not really gonna have enough storage for cooling.
Correct. And it's a big balancing act. So one could argue that, hey, I want less heat pumps, so all you have to do is increase the number of tanks. Theoretically, you could have hundreds of tanks in one tiny heat pump and just let that thermal battery ride for an entire year. Obviously, it's possible you're gonna have to worry about thermal balancing at some point. But to your point, you would be correct that we are finding, well, at least in the New York City market where it's generally cold, whatever you size for a nice heating system, is probably not sufficient enough for a proper operating cooling cycle.
That's an additional.
But vice versa, yeah, it works.
And as you increase the storage side, of course, you're eating into that space advantage.
Yes. The key thing about space is ice tanks are generally, call it, more energy dense. They don't need a lot of clearance area, specifically for airflow. So by and large, the energy density of a tank is a lot better than the energy density of an air source heat pump. So that's a key takeaway.
Patrick, do you want to weigh in on this topic?
I think it's all, I think it's all fair, right? Like, and this is a cop out of an answer, but everything is, it depends, right? Like, as Lindsay said, right, it all depends on what's currently going on with pricing of your utility. It all depends on the building that we're looking at this system in. From an equipment standpoint, everything that we've talked about today is capable of operating in cooling only mode, in high temp heating mode, in ice making mode, right? So I'll challenge you, Richard. Large centrifugal chillers can make ice, right? That was one thing I heard. So it's and I just wanted to put that out, right? So like, technology is out there. All of these can operate whether you're in summer cooling dominated mode, whether you're in a shoulder season where it's heat recovery mode, or whether you are in peak winter where you might be more balanced, but maybe a heat dominated. You have the ability to transfer over, right? So it's going to involve complex controls to figure out how your system operates. But it's not to say that you're just designing a heating only system. You do have the ability to switch over to a cooling system.
Little tricky though, in terms of what you're optimizing for. That's what you were saying, right? That was-
Yes.
yeah. Okay. So questions? In the back.
Yeah, just curious, what our storage
Please, just so we get to know each other, please say your name as your.
Oh, hi, Monty. Are storage source systems, thermal storage systems inappropriate then for the multifamily market where, you don't have a sophisticated operator, you got a super who typically toggles a setting on a heat timer, right? Is this something that's off limits for them? Because we've got to decarbonize the whole city, right? Not just commercial office space.
I guess I could take this one. Right now, we're in the early stages of developing a new innovative solution, and those who can pay for it are the large Class A commercial offices. That eventually, once the system is fleshed out, controls are perfected, automation has come a long way, technology evolves. I don't see a reason why it can't be applied to the residential market. I think the high-rise residential market's gonna be first. And then I don't think it's really applicable for small, like below 2 levels, multifamily. There's probably not enough. It's probably just not enough there to really make this solution any economically viable.
Thank you.
I don't know if anyone else.
Yeah, I'd like to push in a little bit here. And that is not, I don't mean to denigrate your ice storage system at all. I don't fully understand it yet, but what people are doing now is putting mini split heat pumps into multifamily buildings. And this is happening. And there you've got, each apartment gets their own heating system, and they're in charge of it. So the super is, well, he might be called in if something breaks or something, but it's not really his job. There are also multifamily buildings, and the outstanding example is Cornell Tech has a 20-story passive house residential building on Roosevelt Island, and that's got a central heat pump running it with central heat recovery ventilation as well. So these systems are going in. They're not, I won't say, if you want to just, I want to build the cheapest possible multifamily building and make money right away, you're probably going to do gas. I mean, that, you know, that's the sticky thing to do. But if you're worried about what it's going to, how your payback is going to be over the next 20 years, because you're actually going to own the building, suppose you're a university or something like that, then you're going to be looking at electric and trying to find decent large-scale heat pumps for a central system, or going with multifamilies. I know Pratt is considering doing a system such as the one I indicated with circulating water source for heat pumps in the various buildings.
But Dick, I think we could all agree that the mini split case aside, that, you know, when we're looking at a heat pump,
Mhm.
some kind of storage, some kind of thermal storage is an advantage. Whether it's ice or some other form of storage, the heat pump has a difficult peaking proposition.
Yeah, and that's why I was talking mostly about ground source. If you can do that, you're in luck. If you've got a subway tunnel under your building, you're out of luck.
So effectively, the ice storage is a way of bringing a water-based system back into an air source heat pump mode without going to a ground source. But, we'll leave that. There were some other questions out here. Okay, Bob.
Bob Meyer, wondering if anyone on the panel's had experience with capturing the thermal load out of the wastewater stream or even the sewage stream in the street under the building, and how that's integrated into a new design.
So I can maybe feel a little bit of this. We don't have too much expertise in wastewater heat recovery other than just product exploration. There is a product on the market called Shark, where they specifically have designed heat exchangers that can handle the wastewater treatment. Instantly, when we go down that path, we encounter red tape with the city about trying to access the city's sewer system as a form of heat recovery. And that's kind of where it all stops and the solution halts. If we're talking kind of in the building level, yeah, there's smaller products. There's not a lot of heat really in there. It's mostly just going to be drain water. And in comparison to the loads that these commercial buildings need versus what the wastewater produces, it's never going to flesh out financially or viably.
Flush out?
Got it.
So to add to that, because a lot of times this is overlooked as well, I think one of the largest forms of wasted heat within buildings is exhaust air. And a lot of times we think of like energy recovery wheels. But a unique way to look at energy recovery would be looking at like using hydronic coils in your exhaust air stream and using that as a heat source, right? Can you run chilled water to an exhaust air, cool that down, and that's your heat source to then boost up with a heating, right? A water to water product, right? There's a lot of wasted energy there that a lot of times might not be used. The other concept, right, especially within ice heat and storage source heat pump, looking at concepts such as like free cooling is a form of wasted heat, because again, we're under the agreement that we have all this thermal energy stored within the interiors of buildings. If we free cool, yeah, we might not be using a chiller to bring that down, but you're wasting all that heat that you could pull out to then heat your perimeter loads. So it's another way to look at waste, not just our sewage.
So my question is, how would you deploy heat pumps? Steve Eber. Well, how would you deploy heat pumps for steam heated buildings when these buildings don't have sufficient power for the peak load? We have vast majority of buildings on steam. Everything we saw are hydronic loop systems. So my question is, we're gonna do electrification, how do we deal with these steam heated buildings that are almost the majority in New York City?
I can jump on that a little bit, which is that there are heat pumps being developed that can raise steam for industrial purposes. But if they are not very efficient because the lift is so high that you only do it if you really have to have steam. And so most of the projects that I see discussed for conversion of buildings is conversion to either the hot water or the mini splits. And you can talk about conversion to hot water and a central heat pump system if you've got a two-pipe steam system. But if you've got a one-pipe system, you're really kind of stuck.
That's the problem, we're stuck. What you described is beyond what most people can pay. And
Well,
I mean, that's the crux of the problem. I mean, you can put ice, you can do all this stuff, but
it depends on how you're going to look at the pricing. If you're saying it's gonna pay for itself in 3 years, yeah, you're stuck. But if you get a loan carrying out over 20 years that the system is going to be operating in the building and those loans are becoming available, then you're on a different trail. It does become.
there's no savings. You're not gonna be able to get a loan and pay out of the savings because electric prices are 4.5 times what gas prices are on a BTU basis. And therein is the crux of the problem. These rates.
I know one person gave a talk here, Tom Sahajian, about a conversion that he did in a multifamily building on the Upper West Side. And we put in mini split heat pumps, replacing the heating from an oil-fired steam boiler. And the cost of the electricity for a winter corrected for different heating degree days was below the cost of the oil for the steam system in the
True.
preceding years.
Not by very much. I know Tom too.
No, not
by-
much.
Not enough to
Not
make
much.
this project
But-
cost
but-
efficient.
But it did not pay for the, for the conversion. But it's not.
Mike, can I weigh in on this?
At an early stage of rates, I want to let Lindsay weigh in on this question because it's really a rate question.
Well, unlike many of the rest of the people who are in the class tonight, I'm not a complete believer that electrification is right for every single thing in Manhattan. Ponder, if you would, that the boilers that make steam for going into the steam system, suppose they were run on hydrogen or on ammonia. You would have the concept of green steam, no longer having to actually change the equipment in the building, but change it at the source of where the energy is coming from. And that is the central boiler plants in Manhattan by Con Ed that make the steam. If you run them on something that doesn't produce carbon, and if you get that source from something like renewable, such as hydrogen or ammonia, you may be able to basically make green 2,000 buildings at one time without ever walking into any of them by going after the energy that is used to make the steam. Ponder that, and when you think about electrification, sometimes it's better to think way, way, way outside the box.
I think you described the hybrid system.
Go ahead, Steve. Hybrid systems. Yeah, we haven't talked about hybrid systems, which are an interesting.
Put it all
option, too.
in. Works.
Or ammonia. Keep in mind, ammonia is another source that you can make, and may be more cost effective in some cases to mix hydrogen with ammonia or some other type of material which does not produce carbon. And the fact of having 2,000 or more buildings that run on steam in Manhattan, I think needs to be looked at a little more realistically than saying, oh, let's just put heat pumps in everything, because I don't think that makes a lot of sense everywhere.
I do want to take this question though and look at it at the specific segment that you're looking at, which is, the Class A office building, large complex building that's got air systems from a central plant. And just ask in a retrofit mode, and a lot of this installation would be in retrofit mode. What you didn't say anything about the coils. We see that the hot water temperatures are 140 degrees. We're already at a low COP at 140 degrees. Many of these buildings have steam coils. If it's hot water coils, probably designed at 180 degree design. So are we also looking at having to change out all the coils when we do this kind of installation? explanation?
I can answer this. So typical commercial office is hydronic perimeter systems ranging from 140 to 180 degree temperature hot water. These central air handlers are generally speaking, right, 2 to 5 psi of steam, right, whatever 220 temperature. What we've discovered in a retrofit mode is you can take the existing cooling coil and make it into a changeover coil. That is enough sufficient surface and capacity where you can run low temperature hot water through that. So you don't actually have to replace the unit. You don't have to replace the steam coil. You can simply remove it or keep it in there and just simply either retrofit the cooling coil or the pipes and valving, where you can essentially have a changeover where you get that heating with low temperature hot water. That's kind of the prime solution we find if you were to have a heat pump solution with an existing air handler that had steam coils.
And you no longer have to worry about simultaneous heating and cooling.
That's it.
Other questions?
Anthony Stefanelli, New York City DOT. Thermal energy storage, does that work with sites enrolled in like a demand response program where within 24-hour period, we're looking to get under a certain peak demand? Or are you simply kind of just moving your baseline towards the night and then still looking for ways to kind of get under that commitment that you incentivize for?
I think we're gonna give this first to Lindsay to take a crack at. Did you hear the question okay, Lindsay?
Yeah, you know that every building has multiple loads, and your ice storage system is already kind of optimized to minimize demand to begin with. Either that or it's not being run properly. So there's not a lot of space unless you somehow add a bunch of tanks for no good reason to be able to reduce your peak demand more or at a specific time without possibly jeopardizing whether or not you're going to have enough stored ice for the next day. You could say, sure, I'm not going to run my chillers at all, and therefore, be able to reduce my demand for demand response. But demand response is a nice idea. I've done it many times, recommend to many people, but you don't want to do it in such a way that it's going to screw up the value of your ice storage. Your value of your ice storage is to reduce peak demand by shifting that demand to nighttime. If you ever have demand response at nighttime, well, that's a different issue. But normally have demand response pretty much between the hours of about 2 and 4 or 5 in the afternoon where we are. And that's where you've already, for your ice system, avoided the peak. What you do want to think about is how you coordinate the operation of everything else in the building. Do you have the ability, for example, to reduce the lighting levels in hallways and bathrooms and cafeterias and things, so that you do have some demand response that's not connected to your energy storage system? That's where I'd suggest you look instead.
Can I just follow up with a question on that? I mean, is it possible that the combination of all the incentives for demand response would exceed the value of the demand reduction of the ice storage?
Demand response has had a, I don't want to use the word checkered. Yeah, why not? Checkered value. And sometimes we have seen the value of the demand response go up and go down. So I would not want to design a system for 25 years of demand response because I'm not sure how much money I'm going to make in the first 5 or the last 5 of the years of that opportunity. I look at it as being something isolated where you have opportunities to do things that are not going to get in the way with all the phenomenal technological designs you've built in elsewhere.
But once it's designed, you have an option of operating it in response to what the economics are at the time. So you theoretically, in answer to this question, is you could theoretically use it for demand response if that was more valuable, and then use it as peak load reduction for peak demand reduction for the retail rate when that's more valuable.
Let me put it this way. Keep in mind that your thermal storage system is looking at your peak demands month by month. Imagine that you used your demand response system that in effect created an outage, if you will, for available power, and therefore you lost the value of a month of peak demand reduction. That's going to require a lot of demand response activity just to break even.
Anyone else want to weigh in on this?
I'll give an alternate default, right? So a lot of, we have a significant amount of install bases of ice storage plants for cooling applications. Won't name names, we saw a significant amount of them in like the middle teens, where there were a lot of incentives from Con Ed for these demand response programs. So it made sense financially for these companies to lock into contracts, right, for Con Ed to say, you have an hour notice, you have to drop your demand by a megawatt in your building. How do you do that? Well, turning chillers off and just running pumps is one way to do that. I would say currently, we don't see as big of a, right, like a demand response program from Con Ed. We don't see a lot of big interest in thermal storage. Some people still have it, but it's not as much as we used to see. So it does ebb and flow as you, right? It's more of a financial payback.
It is an interesting question that there's kind of a trade-off and a contradiction between going after demand response or peak demand reduction. You know, and if you go after one, it compromises your ability to go after the other. So we are at couple 8 o'clock by my watch, 8:05 by Fred's. I want to give thanks to our speakers. Really interesting topic. I want to say that first watched the Eating with Ice video. It boggled my mind. I watched it 3 times. Still, I've gotten it a bit. It's a really interesting scenario. I think, the inability of the audience to ask specific questions about that is maybe indicative of the fact that it is a little complex. And I encourage you to watch the video again. You'll have the link. Look at the presentations from Patrick as well. It's for that class of buildings, I think it's a really interesting approach and one to have to grapple with. I want to thank you all for this, and we'll continue to look at electrification as time goes on. Thank you.
Thank you. They're very compelling presentations. Thank you very much. Just a couple of announcements. One, don't forget, if you're looking for your CEUs, you see Rob Meyer. We were toying with the idea of in order to qualify for the PDUs, you have to find the layman on the street to make sure you understood this and explain how you will now heat with ice. But we decided to just give out the certificates. Also, if any of you remember that in March, we did a session on macro electrification and just following up on some of the comments about whether we should electrify everything. We did come up with a joint session with NYECC for a presentation of the London Economics updated report on electrification in New York City. So you'll be getting, if you're on the listserv, you'll be getting an announcement of that, which will be taking place on November 10th. Somewhere in the vicinity of November 10th. And we urge everyone to look at that. It should be a real eye-opener. And with that, thank you very much. We hope to see everyone next month. We'll be talking about EV infrastructure. Have a great night. Thank you. Bye-bye.
This is my route. This is my new